We're in Unit 4, and Unit 4 is chemical equilibrium along with solutions. Equilibrium solutions are systems where we have solutions and they're in equilibrium with one another. Always look at their learning objectives. This doesn't all make sense initially, but hopefully you always will come back to the learning objectives at the end of a unit so that you can make sure we've covered all the territories that you see here. Let's go ahead and start with modeling solutions in particulate drawings. So we're doing what is called a microscale drawings of what's happening in solution. And this is a perfect example of how ionic compounds, these crystal lattice structure of ions, will be dissolved by water due to water's polarity. And if you recall, water has these dipoles that go towards the oxygen, and it's bent, and so this oxygen is partially negative, the hydrogens are partially positive. So it's good to know the polarity and the dipole that's going on in water. Now, ionic compounds are fully charged ions, and those fully charged ions, positive and negative ions, are going to be captured by a bunch of water molecules in a certain orientation. So if you look at this negative charge here, this is a negative anion, and that anion is going to be attracted by the hydrogen end of water, encapsulating that ion and pulling it away from the crystal lattice structure right here. Likewise, on the cation end of the ionic compound, you're going to see the oxygen attracted because the oxygen is partially negative, attracted to the fully charged positive cation. That is your modeling to show for how dissolving takes place. We're going to look at the first few examples together, and we're going to understand how solutions work on a particulate level. So here are your particulate drawings right here, particle drawings, microscale drawings. You're going to rank the following solutions in order of increasing molarity. Recall, molarity is moles of solute over liters of solution. Hopefully I've edited this part to show the subscript, moles of solute, liters of solution. So we're going to rank them from low to high. So let's go. So your low molarity, since I'm in yellow, versus high molarity. Okay, looking at the solutions, I should equate the volume. So all these volumes are the same, A, B, and C. D also, but then now I see the volume to be 25 milliliters between E and F. So I know that if I want to equate the volume, that would be twice the volume, which means twice the concentration. And that would put E to have 4 total, and then it also would put F to have 8 total. So there's really 8 particles of solute in there if I equalize the volume. So now, now that we've equalized all the volumes, we can then count how many solutes. Pretty easy to do. You see 4 here. You see 2, 4, 6, 8, 10, 12, 12 here. And then you see 2, 4, 6, 8 here. So there's 8A. 8 and A, and I can write all of that in so that we can remind ourselves. There's 4 here, there's I think I said 12, so 12 here, and there's 8 here, 4 here, and so we can then rank them pretty easily in terms of concentration from low to high of the molarity of the solutions. Let's do that. Low would be, okay, so C, D, and E are all equal. So C, D, and E are equal. Then comes A and F are equal. Oops. And then comes the highest being B. So there's your ranking from low to high. The next question says, how would you prepare 100 milliliter of a 0.10 molar solution of magnesium chloride, starting from a 0.20 molar solution of each? It looks like we're diluting. We're going from 0.2 to 0.1, so you're halving it. So I'm thinking let's use the dilution equation, M1 V1 equals M2 V2, to understand what volume you would use. So calculating from there, your M1 is your original amount of concentration, and that's 0.20. I want to find how much volume of that original concentration I would be using to try to deliver to make a diluted solution that is 0.10 molarity and 100 milliliters of that 1.10. And to calculate without a calculator, I'm thinking to myself, mathematically, since this is halved, that means this is going to be half of this volume. So whatever this volume is, half will give you the equivalence between the two. So my answer is going to be V1 equaling 50 milliliters. So the question is asking us, how would you prepare this amount? So the first thing I'm going to do is I'm going to take this solution that I have. I'm going to take 50 milliliters out of this solution, 0.2 molar, and then I'm going to put it in a flask that has a reading, a volumetric reading of 100 milliliters, and I'm going to add water with that 50 milliliters until it reaches 100. Now I'm going to know that some of the volume is, some of that water is going to cause, because it's a salt, that salt is going to cause volume contraction. So as I'm stirring more water in until that 100 ml is made and no longer is there any more volume contraction, that will then be my total final solution of 0.10 molar of magnesium chloride. So I'm literally going to add water until there's no longer volume contraction, just like your dilution lab from last year when you were doing your dilution of halving the concentration that you see here. Okay. So in solutions, we have a way to measure the concentration of the solution using something called the Beer-Lambert Law. The Beer-Lambert Law is dependent, it's measuring the absorption of light by a colored solution dependent on three different variables. The three variables are molar absorptivity, path length of the cuvette that you are putting your solution in, and then of course C is the concentration. Ultimately, the two measurements that you are really taking out of the machine, the UV spectrophotometer, is the absorbance and the concentration. So the whole idea behind the Beer-Lambert law is the idea that if you have a concentrated solution versus a less concentrated solution, the less concentrated solution is going to absorb less light and then transmit more light through. So more light will travel right through. Whereas a more concentrated solution, like you see here, is going to absorb a lot of that light. So there's a high absorbance, thus less light transmits through. And so we're really going to measure the absorbance or the transmittance of that light. And the way a UV spectrophotometer works to measure that is, first you want to select a wavelength of light that has optimal maximum absorbance. Once you select that wavelength, that light will go through your sample cuvette, which is in a cuvette, that has a certain path length And so that's the path length that you see in the B right here. So there's a certain measurement in centimeters of the path length. And then, of course, the amount of light that gets transmitted through is detected. There's an amplifier and a readout for the absorbance or transmittance from that. So this is a schematic of what is called a spectrophotometer, a UV spectrophotometer. So it actually gives off ultraviolet light or visible light within that range of wavelength. How does a UV spectrophotometer work? So the first thing you want to do is set the wavelength on the UV spec on a maximum for the maximum absorbance or minimum transmittance. So you can either look at max absorbance or the reverse or the inverse of that, which is transmittance for that colored solution. And what you do is you get two different graphs. One is either an absorbance graph, a transmittance graph, or an absorbance graph. I like looking at the absorbance graph because the higher absorbance is exactly the wavelength that you would select and set for the machine, the spectrophotometer, or of course they're inversely related, so the higher absorbance or the lower transmittance is the same wavelength that you would select. So this high peak where that wavelength is, or the low dip of transmittance will be the wavelength you'd select. They will be the same wavelength in the end. And so if you look closely, I'm just going to measure this on this graph and see that it is, the wavelength is, and honestly my eyesight, maybe around 500 nanometers. And hopefully we also see that same wavelength here in the transmittance graph, and it's also 500, okay? So again, you're just looking at max absorbance or min transmittance. Okay, so the second step, after you figured out where are the absorbance, where the wavelength, you select the wavelength for that absorbance, so or minimum transmittance, you then you make your solution. You prepare a series of colored solutions, and this works only for colored solutions because colored solutions absorb different wavelengths of light. If it was clear, then it would transmit everything. There wouldn't be different levels of absorbance. So you're going to make a series of what is called standardized color solution, and that will create what is called a calibration curve. And you use serial dilution to do that. And again, reminder, serial dilution is really looking at M1V1 equals M2V2. In this graph, you're seeing that you're starting off with a concentration of 0.1 molar of whatever colored solution you're looking at, and then 0.08 molar, and then 0.06 molar. So you're creating this linear relationship as you dilute these specific known concentrations, and this is what it means by standard color solutions. Standard means it's a known concentration, and you're measuring that the absorbance of the known concentration. So known concentration. You will hear this word again when you go into titrations as well, which is acid-base, our last unit of the year. So you create this linear relationship that you see here, and this is called a calibration curve. Then you go and do the next step, which is test your unknown. And you test it by the absorbance or transmittance. Once again, you can either do one or the other of your unknown to its precise concentration. And then you can match it up to the calibration curve. So say your unknown absorbs at has an absorbance of 0.5. when you put it in the machine. And so you can take that and move it over and see exactly what the concentration at 0.5 is. And that is, I would say, 0.095 a molarity. So you can do it at any point. You measure your concentration of your unknown solution. Say it's at 0.2 here, the absorbance. You match it up to the calibration curve and you see that here the concentration is 0.3 or 0.03 molarity. So depending on the absorbance of your unknown solution, you can measure the precise concentration using this calibration curve. Okay. Now it is your turn to work through this example problem. This is cobalt 2 chloride that you're running through the machine, the UV spectrophotometer. And cobalt 2 chloride, the cobalt ion, 2 plus ion, is a blue solution. And these are the various different concentrations that is diluted to make your standardized solution. And this is the data output for all of this data that you're that this scenario entails. So go ahead and do this problem. Check your answer on the bottom. Work through it yourself. Make sure you're trying to figure out how to process Beer-Lambert's law in UV spectroscopy. Okay, so here begins equilibrium. And from here on out, we're just going to do equilibrium. So there's two types of reactions. Reactions that go to completion and usually involves a limiting reactant. And the type of arrow that comes off of a reaction like that is a singular one-directional arrow. So reactions that go to completion are singular one-directional arrow. Whereas there's reactions that are reversible. And those reactions reach equilibrium, and the two double-sided head arrow, or like a half arrow going one way or a half arrow going the opposite way, is a reversible reaction that reaches equilibrium. I'm going to show you the difference in the graph of the concentration versus time graph between the reaction that goes to completion versus the reaction that reaches equilibrium. And we're also going to model it. So here's a simple generic reaction. A, again, notice the one-directional arrow going to 3B. So we start off with a certain amount of A, and in this case it's 2 molecules on a microscale. And then notice how A reacts really quickly going down, but then not quickly, but it's going down until it reaches 0. And you know that A is going to run out. B increases 3 times. Look how fast that is. Until, of course, when A runs out, B stops being made. That's what you're seeing over here. So say you have 2 A's. You start off with 2 A's. You know that every A makes 3 B's. So this A is going to make this 3B, and then of course this A is going to make 3 of these B's. So essentially the reactants will run out. So I will cross this out to show that all your reactants is gone to making 6B here. Unlike a reaction that goes to completion, a reversible reaction that reaches equilibrium is going to show a double-sided arrow, and it's the same reaction, but now you'll notice that at equilibrium, even if you started off with 2 A's here, one of the 2A forms 3 B's, but notice how the reaction will go reverse as well. So you're seeing a reaction that always has both reactants and product at a point called equilibrium. So let's go ahead and draw what that would look like. Let's go ahead and graph A and B in terms of concentration versus time. A is going to decrease and then it levels out. B is going to increase 3 times. So I really wanted it in blue. So you can see B. B is going to increase 3 times and then it reaches also equilibrium. So there's a point called where both concentrations of reactants and products reach equilibrium, and that is when they're constant. And you can see it when you see a flat line right here where the concentrations remain constant. So I'm going to take that and highlight where I see equilibrium starting. So this is when equilibrium starts. And why this doesn't go to zero, why A doesn't go to zero, is because B is reforming A and then A is reforming B. And of course, when the rate of the forward rate equals the reverse rate, you have what is called chemical equilibrium. It's a very steady state of A staying constant as well as B staying constant in concentration over time. Okay? Now, because A and B, reactants and products, remain constant over time, we actually can ratio the products over the reactants. And when we ratio that, we get a constant value called the equilibrium constant. But let's go ahead and compare with equilibrium versus completion. Let's see what's happening as we go through this actual chemical reaction. The chemical reaction is N2 reacting with H2 to form, or 3 moles of H2 to form in equilibrium with 2 moles of ammonia. Okay, so the first part of the reaction, you initially have concentrations of your reactants, N2 and H2. The rate of the forward reaction is quite quickly occurring during that time. So let me go ahead and draw it on the graph as well so we can see that rate. As time goes by, you're going to see N decreasing, and then it reaches a point of flat line here. And then H is also decreasing, but faster, 3 times as fast. Then it also H is also flatlining, where N flatlines. B, or ammonia, is going to increase with time, and it's going to increase twice as fast. Now, when ammonia increases, you're going to see ammonia also continue to break down. And once again, they flatline all the same time, okay? And so equilibrium is going to occur once again at the spot where all 3 of them, all ammonia, nitrogen, and hydrogen, flatlines. Now, we discovered in terms of the reaction, the forward reaction, the rate is going to depend on the concentration of how much you have of the reactants over time. So that's where you see we discovered the forward rate to have a rate of a constant of some sort times the concentration of N2 and then the concentration of H2 to the 3rd power. So we discovered this experimentally as far as the forward rate. Now the reverse rate, so as N2 and H2 are used up, concentrations decrease. So the forward rate slows down over eventually, and you can see the slowing down as you see this flat lining here. Some of the NH3 is produced, and then a reverse reaction starts to increase. That reverse reaction is ammonia decomposing into nitrogen and hydrogen. And of course, the rate of that reaction is going to be dependent on the ammonia, the reactants, which is the ammonia, to the 2nd power. Now, when you look at the rates of the forward and the reverse, F stands for forward, R stands for reverse, and you set them equal to each other, like you see me doing here, setting the forward and the reverse rate equal. You then set their concentrations also equal. You create eventually this product over reactant ratio where it's all the products raised to its stoichiometric coefficient. So notice ammonia is raised to the 2nd power, which is the same stoichiometric coefficient here. Nitrogen is also raised to the nitrogen is raised to the first, just like its coefficient. Hydrogen is raised to the third, just like its coefficient. So you create what is called the rate law, or I'm so sorry, the equilibrium constant. So this is Keq. And so Keq is a ratio of products over reactants raised to their stoichiometric coefficient. Looking strictly at the model here down here, it's healthy for us to always see what's happening on a microscale. If you look at the Keq equilibrium expression, it's ammonia squared over nitrogen to the first power and hydrogen to the third power. The constant itself is a pretty small value, which means there is a lot more reactants than products. And so what you see in here is just that. There is a lot more reactants than products overall in this equilibrium, or in this container, at equilibrium, that is. So you look at the constant as a way to see if, hey, is this number big or small? If this number is small, you know that there are more reactants than there is products. So this is again products, reactants. And exactly what you see in this equilibrium system. You see there are more nitrogen and hydrogen than there is ammonia. Okay, so we came up through experimentation of different reactions, we came up with this equilibrium expression, and it's actually called the law of mass action. I'm not going to go into the term, but it's an expression. And the expression we found is because the concentrations of reactants and products remain constant, we can ratio the products raised to their stoichiometric coefficients and then the reactants on the bottom of the ratio. And that is called our equilibrium constant, and this is the expression. The constant is an actual number. C is in concentration. So these brackets actually represents molarity concentration. And this K constant is actually mucho temperature dependent. I wouldn't whip out my Spanish and my very limited Spanish unless, honestly, it's important. So it's very temperature dependent. So K only changes when temperature changes. The one thing that you want to note is pure solids and liquids have no effect on the equilibrium. So the concentrations and partial pressures, are constant in a reaction. And when we say constant, we treat it as though the concentration is 1 molarity. When you plug 1 molarity, like if you put the solid into this expression and it's 1 molarity, you're going to see it equals whatever other number is there. So that's why we treat it as 1 molarity. I tend not to even put solids and liquids into the equation or the expression because it just would start to add one more layer of confusion into it. Just exclude it altogether. Pure solids and pure liquids excluded out of the equilibrium. Another equilibrium expression and constant is for gases. So gases have their own expression called the Kp. P stands for pressure, usually in atmosphere. So it's another constant, and once again, these are all gases, and you're seeing Kp apply to only gases. So these have to only be gases in order for you to have an expression for it. If you had solids and liquids or aqueous substances in there, you would not include that in the Kp expression nor the constant itself. Just a really quick, I forgot to mention, C stands for concentration here, so you're looking at equilibrium concentrations in molarity units here. EQ means equilibrium. So to make a quick little summary of Kc and Keq, it's a constant. Characteristics of chemical a reaction relates to specific concentrations of reactants and products at equilibrium at a given temperature and pressure. So again, it's a reminder that K is very temperature and pressure dependent as well, but really temperature dependent in terms of the constant value. Now we get into just understanding the relationship of what K is, relationship in terms of its ratio. So if you have a KEQ that's really big, that means at equilibrium, you favor the products. And it really does make sense because for you to have a big KEQ, that means you have a lot of products compared to reactants. So there's a lot more to get you a big ratio for KEQ. Now, if the KEQ is very, very much bigger than 1, what you're saying is really there's essentially the reaction is going to completion. So that means R is nearing 0, and of course there's a lot of products leading to a very high KEQ value. If the KEQ is 1, that means at equilibrium, there's really kind of like an equal amount of products and reactants. Now, all of these are all equilibrium states except for this really big greater than 1 situation. So this is just saying, hey, at equilibrium, you're going to have equal amounts of both products and reactants, and that's why you have a KEQ that's 1. If the KEQ is less than 1, that means there's a whole lot of reactants compared to products. That's why your ratio ends up being a lower KEQ value. So a very small amount of products compared to reactants. Reactants dominate basically at equilibrium if your KEQ is less than 1. Okay, so let's go into another idea. Q is no different from K. QC, which is for concentrations, is the same form as the equilibrium Kc, except it involves specific concentrations of both reactants and products that are not necessarily at equilibrium. So what we like to do is compare Q to Kc and know whether this reaction lies to the reactants or the products, and whether the reaction is going to try to get to equilibrium by shifting a certain direction, whether it's the forward or reverse, or it's at equilibrium. Okay, so K doesn't look very different from Q doesn't look different from K. It's pretty much the same thing. Again, these concentrations are not necessarily concentrations at equilibrium. So what happens when Q is less than K? If Q is less than K, that means you need to increase Q to get to K. So how do I increase Q to get to K? I need more products. More products will lead to increasing Q to become K in order to reach equilibrium. So we're going to forward, your equilibrium is going to try to, in order to get to equilibrium, the reaction in the forward direction, in other words, forming more of C and D, will give us more products, increasing Q in order to get to K. Now, if Q equals K, that means we're at equilibrium. So you're currently at the equilibrium state. So Q is just a metric of knowing where you're at in a reaction, whether you're before equilibrium or after equilibrium, but there's no really before or after. It's just what do you need to do to the amount of products compared to reactants in order to reach equilibrium. If the Q is greater than K, that means you've got a whole lot of products compared to reactants. So that means you need to pump up. That means you need to pump up the reactants. So the reaction is going to try to favor the reactants, making more reactants in order to reach equilibrium. Finding the equilibrium expression as well as the K constant in a reaction requires a few general rules. And so these are just rules that you have to adopt to know what to do when you work through an equilibrium reaction as well as a K constant. So here's if I take a reaction, an equilibrium reaction, and I flip, or here's my original one, sorry. And so the products, to write the expression is just to take the products divided by the reactants. And that's what you're seeing here, the concentration of the products over the reactants. Now, if you flip that reaction, so what happens to K when you flip that reaction? Well, now you've taken the inverse. So now that K is the reciprocal of K. So whatever your K value is, you take the reciprocal, and that is how you what happens when you flip the reaction. What if I double the reaction? In doubling the reaction, what you've done is you squared everything, because equilibrium, or the way K works, is you're taking the products over the reactants raised to their stoichiometric coefficient. By doubling the reaction, you've really changed the stoichiometric coefficient. So in this case, you're squaring everything. Now, the next one is you're halving the reaction. By halving the reaction, you're basically, instead of squaring the reaction, or K as well as the expression, you're going to square root K as well as square root the expression. Now, when you're adding up equilibrium reactions, what you're going to do to the K is you're going to multiply them. So whatever the K is for one reaction versus the K for the other, you just multiply them as you're adding these equations up. Notice A plus, when you add the reactants, it forms AC, and then add the products, forms BC. Still equilibrium. The constants and the expressions end up multiplying together, giving us B over D divided by A over C. And the constant also divides as well, multiply together as well. So here's a problem, and we'll walk through it together. Okay, in example number 4, it's asking what is the equilibrium constant for the equilibrium reaction. So here's a reaction that's at equilibrium, and we want to be able to find the constant for this reaction. And they give you a series of other reactions with their constant and expression. So here we have the barium sulfate, and they give you the KSB for that reaction. We also have barium hydroxide, and they give you the KSB for that reaction. You'll learn about KSB in a couple of pages down at the end of this unit. And so the reaction for KSB, any KSB, is taking the solid and making the ions that make up that solid. So dissociation of that solid in water. Same thing here. KSB is the solid, barium hydroxide, breaking up into their corresponding ions, cations and anions. The expression for each of these are, again, products over reactants, and you wonder, where did the reactant go in this expression? Well, it's a solid. You don't count solids in the expression nor the constant. So that's why you're not seeing that. And of course, it's the same here. Products raised to their stoichiometric coefficient. The 2 is right there. And then over the reactants. But this is a solid, so solids do not count in that. So the expression are these two expressions, and of course the constants are given to us based on what was given in this problem. Now the first thing I want to do is I'm going to take these reactions, and these two reactions, and I'm going to try to align it with this equation right here, this equilibrium equation, because I want to find the constant as well as the or just the constant for this equation. And when I say align, what I'm doing is I'm sitting here going, okay, here's barium sulfate, solid. It's on the reactant side. Here's barium hydroxide, solid, on the product side. So I'm going to make sure these two are aligned, and so I'm going to have to flip this reaction right here, the barium hydroxide. And that's precisely what I do. I flip that reaction. Upon flipping that reaction, and then leaving the barium sulfate equilibrium reaction as is, notice when you add these two reactions, you're going to get the exact reaction that you see up here. And that's the goal, is to do that. Now, what does it do to the K expression as well as constant when you flip a reaction? Well, up here, when we flip a reaction, everything is reciprocated. So we take the reciprocal of the expression as well as the constant. And that's exactly what I do here. I take the reciprocal of whatever that expression is, which is 1, now becomes 1 over whatever that expression is, which is the concentration of barium at equilibrium as well as hydroxide at squared at equilibrium. And then I also would reciprocate the Kb constant as well. The barium sulfate equation stays as is, as well as its constant. Now, in order for me to get this reaction, I had to add these two reactions together. So upon adding that, I get the same equation. So that means I'm going to have to add, or I'm not going to add the constants. What happens when you're adding is you have to multiply. So that's the weird part. So multiplying these two expressions will give me, in the end, the barium will cancel out, and then leaving me with sulfate on top and then hydroxide ion squared. So this is my end result, as far as the expression is concerned. Now, again, adding these equations also will multiply these two constant, which I had already reciprocated here. So I'm multiplying, reciprocating, and then multiplying. And that's exactly what you see here. I took the reciprocal of the second equation, and then I'm multiplying. Now doing that will give me my new constant. So this is my new constant for this reaction right here, the equilibrium constant. And my expression totally matches up with exactly what this equation is. And I know I've done it right when the expression aligns as well. And you're going, but Mrs. No, what happened to the solid? These two solids are solids. They do not count in the equilibrium. So notice product over reactants to their stoichiometric coefficient. Reactants, stoichiometric coefficient. So this is the final answer and the expression. I always do want to work out the expression to make sure it aligns with the equation that I desire to have, or I would like to have in the end. Okay. Now, much of what I'm doing is teaching all the content, and then we're going to practice afterwards. So we're going to get into now Le Chatelier's principle and equilibrium. So Le Chatelier's principle states that if an external pressure or stress is applied to a system at equilibrium, the system will adjust in such a way that the stress is partially offset as the system reaches a new equilibrium position. Note, only stresses that change the Kc or Kp will affect the enthalpy of the reactions. And we'll talk about that will be affected by the enthalpy of the reactions. So in other words, anything dealing with temperature will impact this K. We'll again talk about that later when we get to the temperature stress. And so there's different types of stresses. One of the stress is concentration. There's also stresses with pressure and volume, and that only applies to gases, of course. And then there's also stresses with temperature, and that will definitely change the Kp or the Kc of a problem. Let's first talk about concentration. That's one of the easier ones. Okay, so here's a equilibrium reaction, and then I did the expression as well. It's products, NO2, raised to its stoichiometric coefficient, reactants, N2 and O2, raised to their corresponding stoichiometric coefficient. So the 2 right here, we raised it. Okay, so this is the equilibrium expression. Now, I'm going to stress this system out. Now, I'm going to describe stresses really quick. If my body is in equilibrium also, it's called homeostasis. When I am talking a lot, for instance, in this video, I'm talking a lot, I am now thirsty, so I stress my system out. by talking a lot, and now I'm thirsty. Thirst is my stress. What do I want to do? To undo the thirst, I need to hydrate my body. And so I'm going to find a way to get back to equilibrium by doing the opposite of what that stress is. Why am I talking about that? Because in a system that is stressed, like you see here, it's going to find every way to try to undo it by subtracting the N2. How do I subtract the N2? Well, I move away to make consuming the N2 to make NO2. So I'm going to go away, and going away means I'm going to go forward. So the direction that the reaction will shift is in the forward direction, making more of the products, making NO2 here. Now, what is happening when this stress is occurring? Well, my Q is less than my Kc. How do I know that? Well, that's because my Q, I'm going to write that down. Q is products over reactants. So if I'm adding more N2, I'm adding more reactants. If I'm adding more reactants, that's going to cause my Q to go down. And that's exactly the scenario that is currently outlined here, which is I'm adding more reactants, N2, which is a reactant, causing my Q to go down. That's why Q is less than Kc at this point. In order to reach equilibrium, I'm going to need to make more products. Making more products will increase your Q to make it equal to Kc. So this is trying to, again, I'm not at equilibrium, I'm trying to get to equilibrium so that they can be equal, these two equal. So in order to do that, I'm going to increase the products to do that. Let's go to adding O2. This is a stress, bad thing. So you're going to find a way to decrease the O2. How do I decrease the O2? I'm going to shift it forward. So I'm going to shift the reaction to go forward. By shifting the reaction to go forward, I'm making more products to try to get Q to equal Kc, and that means the forward direction will speed up until I reach equilibrium again. And when I reach equilibrium, that means my reactants and products are constant and the forward rate is equal to the reverse rate. So this whole forward and reverse is talking about the rate. The forward reaction rate is going to increase until the forward and reverse equals one another, which means Q equals Kc. At equilibrium, you've reached equilibrium. Now the other stress. Here's another stress. In this scenario, the stress is adding NO2, nitrogen dioxide. In doing so, your reaction is going to try to get rid of nitrogen dioxide. To get rid of nitrogen dioxide means you're going to make more quickly of the reactants. Making more of the reactants means the reaction in the reverse direction is increasing. The rate of the reverse is increasing. In this scenario, the Q is greater than Kc, which means there's a lot of products, and that's because you've added NO2, which is a product. And to reach equilibrium means I'm going to need to make more reactants to try to get Q to equal Kc. So this next stress is about pressure and volume, and it only impacts gases. So gases exert pressure in a specific volume. The two scenarios we're going to look at is when the moles of gaseous reactants do not equal moles of gaseous products, or in this case products and then reactants, it doesn't matter the order, or when they're equal to each other. We'll see what happens, okay? So we're dealing with gases, and so you'll notice that these substances will be gases. So I'm going to really do the Keq expression. So it's partial pressure of ammonia raised to the second stoichiometric coefficient, and then partial pressure of nitrogen raised to its stoichiometric coefficient, which is 1. And then hydrogen raised to its stoichiometric coefficient, which is 3. So again, these are stresses. Stresses are bad. We're going to try to undo the stress. To start these problems, what you do is you count your moles of gaseous reactants and moles of gaseous products. And what that means is you count them literally in the balance equation. There's 3 moles of hydrogen gas, 1 mole of nitrogen gas. So I would write down 4 total moles of gases. And in the product, 2 moles of gases. If my reaction shifts forward, I am taking 4 moles to try to create 2 moles. So I'm decreasing the pressure when I do that. So I'm really aiming to decrease pressure because 4 moles of gases are forming 2 moles of gases. If I go the reverse direction, what I'm doing is I'm trying to increase pressure. And how I know I'm increasing pressure is I'm seeing 2 moles create 4 moles quickly. So that is increasing pressure when less moles become greater number of moles here. So that should set us up pretty well for all these stresses. So the stress that I'm going to do on this system is I'm going to increase the pressure. So once again, which means I'm decreasing the volume. So I'm taking the container volume and decreasing that container volume, which increases the pressure. Now, what your immediate reaction is to do is to try to find a way to decrease pressure because you're wanting to undo the stress. So you're going to do the opposite of whatever the stress is. Just like thirst, I'm going to make sure I drink water. I didn't sleep well last night. I'm going to make sure I sleep well tonight. So you're trying to always undo whatever stress your body or your system is undergoing. So how do I decrease pressure? Well, decreasing pressure means I'm going to shift forward because 2 moles will become, or 4 moles will become 2 moles, which will help to reach equilibrium again by decreasing the number of gases formed. And that's why the reaction is going to go forward. The other stress is the opposite, which is you're decreasing pressure. So you want to try to increase pressure. So you go to the reverse direction. The reverse direction, like you see here, is going to create more moles of gases quickly to try to reach equilibrium. The Kp would all work the same way. Again, Kp less than, if you have a K or Qp less than Kp, that means you're going to have more products or more reactants here in order to reach, and less products. So in order to reach equilibrium, you're going to try to up the ante in terms of the products so that you can get Qp to equal Kp. Likewise over on the bottom below that, same logic, okay? Now we get to a scenario where the moles of gases actually are equal to one another in the reactants and products. So here I have my products and reactants, and I'm going to count how many moles of gases. It looks like I have 2 moles of gases here. 1 here, 1 mole here, and 1 mole here, giving me 2 moles of gases. And then over here, I also have 2 moles of gases as well. And I'm going to emphasize the word gas there so that I know I'm counting gases and only gases. Sometimes I might have a solid in that reaction, so I'm going to be very careful. So in the case where you're stressing the system out by decreasing the volume or increasing the pressure, what you're going to notice is there's no way to compensate for that increase in pressure. You can't shift forward, you can't shift reverse. It's actually going to cause the whole system to increase in pressure. So that's why the equilibrium system can't do anything to compensate, and thus you see no change. No change is the response for this scenario. And again, the Kp is already equal to the Qp is equal to Kp already in these two scenarios where you're seeing either an increase in pressure or a decrease in pressure. Let's move on to the effect of temperature. When it comes to temperature, what you must do is you actually have to look to see if the reaction is endothermic or exothermic. We know that if the delta H is negative, that means it's exothermic. So heat is going to be on the product side right here. So I put this little triangle which represents heat. And I'm putting it in the product side. If the delta H is the enthalpy, the change in enthalpy is positive, that means the reaction is endothermic, which means heat is on the reactant side, like you see here. Now this is, I'm using Kc as the basis for this equilibrium reaction. Once again, I'm increasing temperature. So what do I want to do? I want to find a way to undo that by decreasing temperature. How do I decrease temperature? Do I go forward, making more heat? Or do I absorb that heat and go reverse? And you're right to say that you want to absorb that heat. The reaction is exothermic going this way, endothermic going this way. So the reaction in the reverse direction is absorbing the heat. And that's exactly what you want to do. You want to absorb that heat in order to try to alleviate the stress right here, the stress of increasing temperature. Now we get to decreasing temperature. If you're decreasing temperature, the reaction wants to increase the temperature. How do you increase it? Going in the exothermic direction. That means forward. And that will produce more heat if you go forward. When you look at endothermic, you put the heat on this side. Increasing temperature is going to stress the system, so you want to find a way to decrease temperature. Decreasing would mean absorbing the heat, so you're going in the forward direction. If the stress is decreasing temperature, you're going to try to increase temperature by going in the reverse direction, so more heat is produced. And you can, of course, figure out the Q related to the Kc during these moments. And how it's going to try to find a way to equal. Q wants to equal Kc in the end. And it's going to try to reverse, the reaction is going to change direction or speed up a certain direction in order to do that. Now if you add a catalyst, adding a catalyst will not affect the equilibrium system. To shift. It's not going to cause it to shift in any way because the reaction is going to speed up the forward rates as it does the reverse rate. So it will cause the system to reach equilibrium even more quickly, in essence. So adding a catalyst means that equilibrium system is already at equilibrium, so there's no change in essence. Adding a pure solid or a pure liquid, since pure liquids and pure solids have a concentration of 1, it's not going to impact the equilibrium at all. So the stress of adding liquids, pure liquids or pure solids, you're going to see no change to the equilibrium system. No compensation needed in order to reach equilibrium.
The question is, why do solids not affect equilibrium? So right now, the system that you see in here in this vessel is at equilibrium, and you know it because you see that the 5 gas particles or carbon dioxide molecules that you see floating around stays at 5 over time. So in other words, it's 5 right now.
10 seconds later, it's still 5.
10 seconds later, it's still 5. So it's actually staying constant. The concentration of that carbon dioxide is staying constant over time. Now, you also notice some calcium oxide as well as calcium carbonate. That's in green. Calcium oxide is in orange. When I add, and by the way, this system's at equilibrium, and aside from the concentration, there's an arrow on this. There should be a double-headed arrow. So imagine the arrow going the other way as well, the reverse direction. As I add more calcium oxide, watch to see what happens.
Does that change the amount of carbon
Does that change the amount of carbon dioxide? It's still 5, right?
It looks like adding
So
more
it looks like adding more solid to a system that's at equilibrium has no impact on it. So if I add more or take away, you're going to see that it's not going to impact. Likewise, for calcium carbonate, which is also a solid, so these two are solids, you're going to see that it has no impact on the system. And you would see impact if you saw amounts of carbon dioxide changing.
Adding more
did not do anything. Notice adding more calcium carbonate didn't change the amount of carbon dioxide. So hopefully the takeaway is knowing that solids added to a system at equilibrium is not going to impact that equilibrium system.
Now we're going to do FRQ1 together. And so we set up by reading the question very carefully. So take about a minute to read the question. As you're reading the question, I'm going to set up from the information from this question. I know that delta H is negative. So it's the reaction's exothermic, which means heat is added to the product side. I also know my moles of gases, so I'm going to count my moles of gases to see how many moles of gases in the reactant and the product. And it looks like I have 3 moles of gases in the reactant and 2 moles of gases in the product. So let's go ahead and read what the first stress is. It looks like a stress situation because A is decreasing the volume of the system. Decreasing the volume of the system means you're increasing pressure. What will the equilibrium system do in order to compensate for that stress? And so it looks like it's going to find every way to decrease pressure. So the opposite of increasing pressure is decreasing pressure. So it's going to move to the lesser moles of gases. Upon moving to the lesser moles of gases, you're shifting in the forward direction. So it's a forward shift. Forward shift means the reaction is going fast forward. If it's going fast forward, you're making more of the product, which is SO3. And no effect on Kc because this is not a temperature change. Temperature change is the only thing that will affect Kc in the end. Now we go to B. In B, what you're seeing is the stress is an adding of oxygen to the equilibrium system. So oxygen's right here. Adding more, you want to try to decrease if you're adding more. So shift to the forward direction will decrease that because you're consuming oxygen. So forward shift. And forward shift, as we can see, means more sulfur trioxide is being made and no impact to the equilibrium system. Now we go to the last stress. The last stress is raising the temperature of the system. That is going to increase stress. It's going to cause stress on the product side. So you want to try to absorb that heat. And to absorb is to go in the reverse direction. Remember, exothermic in the forward, endothermic in the reverse. So we're going to reverse shift the reaction. Upon reverse shifting, that means you're going away, you're making more reactants quickly and consuming the product. That means SO3 decreases as you're moving fast in the reverse direction. Now what happens to Kc? Now let me go ahead and make sure I define Kc. Kc is products over reactants. By reversing, that means reverse shifting, that means you're going to make more reactants and you're decreasing the products. That's why SO3 decreases. What that does to this ratio of products over reactants is if I take a small number and divide it by a big number, I get a small Kc value. And that small Kc value means my Kc is going to decrease. My equilibrium constant is going to decrease. So notice how the only thing that will change your K constant is any changes to temperature, because temperature is mucho dependent, or Kc is mucho dependent on temperature.
So this is a continuation. Make sure you check your answers, as always. This is a continuation. Go ahead and work through FRQ number 2 and check your answer. All right, now we get into the mathematics of calculating Kc and Kp. Not through using equations that are given to us, equilibrium equations, a series of equilibrium equations. We're actually going to calculate using ice tables. So this was actually the initial intent of teaching an ice table, is to work out equilibrium problems. Reminder, ice stands for initial, change, and now instead of excess or equals, or in the end, it actually stands for equilibrium. So at equilibrium, we should expect to see amounts of both reactants and products present. And so here is an example of how to work through an ice table. So oftentimes in equilibrium, you start off with initially a certain amount of reactants. You don't have any products. So 0, 0 for the products. Some change occurs where you're reacting some of the reactants, and of course, stoichiometrically, you consider how much of the reactants you form. So every 2 moles of the ammonia, so you're losing twice as much to form X and then 3X here. So this is the plus. You're forming your products and then so at equilibrium, it's just adding up these sections here. X and 3X. And the expression as we know it is Kc. I'm going to do the Kc expression. And I always do expression so that I remind myself that for hydrogen, I'm going to have to cube that. For ammonia, I have to square that. Square that equilibrium concentration. So with that expression, I then just plug my numbers in. My Kc is given to me. Sorry, I was supposed to plug Kc in. It's 2.37 times 10 to the negative third. And then my ammonia or nitrogen is X. My hydrogen is 3X cubed. Notice how your problem is getting complex here, mathematically. And then for the concentration at equilibrium, this is it. So all I did was I plugged in my equilibrium amounts into my equilibrium concentrations and raised them to their stoichiometric coefficients. And that's what you're seeing here. And I plugged in Kc as well, because that was given to us at 72 degrees Celsius. Now this problem looks really complicated, and if you think about it, it's going to be a x to the 4th power. And so polynomials, this isn't a polynomial equation in the end. The most that you've done in, I think, up to Algebra 2 is x squared as the highest degree that you're seeing. But this is x to the cubed, or sorry, x cubed times x, which is x to the 4th power. You don't usually see that. And so there's several ways to go about solving these equations that are complex like you see here. Oftentimes you'll get a polynomial that is raised to the highest degree of 2. And usually you use the quadratic formula for that to solve for x. And that's what we're trying to do, is solve for x in the end. The other way is something called the approximation method. And when that happens, I'm using a very generic scenario right here. What you do is you assume x is very small. This is actually an easier way than to use the quadratic formula. When you make the assumption, the approximation that x is so small that you can get rid of the x that is subtracted here. And it's smaller compared to the 0.112. So if it's so small that it's near 0, you can zero that out. And so then you can solve quite easily when you have an equation where you don't have this term right here. And you can just solve for x. When you do that, when you use the approximation rule, you actually have to validate and make sure that x is so much smaller, it's less than 5%, compared to the number that you're subtracting from that x, which is 0.112. And when you do the approximation method, you really do have to do a percent comparison. And so you find x, you solve for x in this instance, and then you compare it to the original amount that you zero the x from. So the amount is 0.112. So that's the initial compared amount that you assumed x is small comparatively. And then you times it by 100, and then that will give you a percent. That percentage needs to be less than 5% in order for us to be able to say that x is quite small. Let's actually get into working through an example problem with equilibrium with numbers and such, and we'll go through and see why, although the quadratic formula might give a more precise x value, solving for x, in other words, it will eventually allow us to solve for the concentration at equilibrium. The approximation method is a faster way to do it, and of course the validation is quick and easy as well. So let's go ahead and look at this problem. If we have 6 moles of C2H6 and 6 moles of Cl2 originally in a 3-liter container at 10 degrees Celsius, determine the equilibrium concentrations of the reactants and products. The Kc for this reaction is 0.1 at 10 degrees Celsius. Use both the quadratic formula and approximation method to solve and figure out and see the difference. So here I have an ice table. This was kind of misaligned. So the first reactant, second reactant, first product, second product, okay? Now I notice that this is a solid right here, one of the products, so I'm going to cross that out and not include that in the equilibrium. I do know my equilibrium expression is going to be products of reactants, so I always start off with doing my expression. It's one of the easiest things for you to do, and it's a great habit to have, to embed into always writing an equilibrium expression. That way you remember what's being raised to what power in terms of stoichiometry. So this is a pretty simple, everything is raised to the first power. Now, the first thing I want to do is I have to set up my ice table and put my initial amounts in. When I take my moles and divide it by my liters, that will give me my molarity. So I do that for each. 6 divided by 3 is going to give you 2.0, figging it, of course, molarity. And I do it also for chlorine gas. Upon doing that, and 0 is my product. Remember, initially I have my reactants and I have no products. I lose some of that. I lose some of my reactants. I don't know how much it is. I will figure it out with the equilibrium expression and constant. And I make some of my products. And so at equilibrium, you just add up these two columns and you'll see it's 2.0 minus x. Same thing here, 2.0 minus x. At equilibrium, these are the amounts that I have. So then I plug it into my expression here. And upon plugging all the values and constants at equilibrium into my expression, I get given to me that Kc is 0.1. I get X, which is my concentration of HCl at equilibrium, as I see here, divided by these two multiplied here. My reactants basically multiplied. And it looks like when I multiply my reactants, I'm just going to square it pretty much. That's what both of them multiplied look like. So here's my overall mathematical equation. Now I'm going to do math. From here on out, I'm just working through the mathematics of this problem. I'm going to go to the next page to do that. So, once again, this is my expression and my equilibrium amounts of my reactants and my products and my reactants. And it equals my Kc value. If you recall in math, what you do when you have binomials multiplied by each other, you're going to FOIL it, okay? And so I'm going to do some foiling. So x on top, first times the first is 4. The outside 2 is 2x. The inside 2 is 2x. Last times last, x squared. And that equals 0.10. Okay. I can easily simplify these two terms. This is minus 4x plus x squared and 4. And over x equals 0.1. And so I am going to cross multiply these two and this one, which gives me x on one side. And that gives me 0.4 minus 0.4x plus 0.1 x squared. And then of course I'm going to bring the x over so that everything equals to 0. So when that happens, I'm going to rearrange the equation. I'm going to go and try to get my highest degree in front first. I'm going to minus, and so when 1x is being subtracted over to here, you get minus 1.4x. And then 0.4. So according to my quadratic equation, you've got ax squared plus bx plus c equals 0. I know how to plug it into my, I can easily plug it into my formula knowing my a, my b, and my c. So here's my a, my b, and then my c. So plug that into the quadratic formula, and this is what you yield in the end on the side right here. Now, from there, you've got two roots that will be forming out of this because of the plus and minus right here. And here are the two roots. One root will be absurd, and so I can tell it's the absurd one is the 13.7. Why? Because my initial concentrations were, I believe it was 2.0. You can't have any more than what you can't end up with more than what you start off. So this here is my absurd root. This is my correct root out of the two roots from the quadratic formula. And I'm going to plug it into my ice table. If this is my x here, I'm going to then plug in and get my concentrations of both the C2H2 at equilibrium as well as HCl at equilibrium as well as Cl2. Again, I'm going back to my ice table and just plugging in my x here to each of those amounts. Now let's go ahead and see what happens when we use the approximation method. In the approximation method, what we're going to do is we're going to assume that x is very small. If x is very small, that means you have 4 in the bottom. And with 4 in the bottom, you then can solve for what x is. X is 0.4. Now, of course, this x is more precise than this x, but ultimately, you're not far off. Look at this value at equilibrium from all these values that you see. Now, you do have to assume, make your assumption. You do have to go through the validation process to make sure that the 0.4 is actually less than 5% of the 2 that you subtracted x from originally. So we're going to go ahead and calculate and validate that. It's a very simple process. You check to see if x, as it compares to 2, is less than 5% when you take a percentage of that. And so take 0.4 divided by 2, you end up with 20% in the end. And because this percentage is greater than 5%, you have to use the quadratic formula. So you actually have to go back and take the values for x from the quadratic formula, which is right here. Most of the time, though, approximation method is going to work. You're going to see less than 5% value for x compared to the subtracted number that you subtracted x from. And most of the time, you wouldn't have to go to the quadratic formula because you're not expected to remember or use the quadratic formula for these problems. All right, let's go to example number 6 and let's see how this plays out. That was all hypothetical situation. Let's actually see a real equilibrium problem play out. So, at a certain temperature, a 1 liter flask initially contained this many moles, 0.298 moles of PCl3 gas, and 0.00870 moles of PCl5. After reaching equilibrium, this is the amount that was found in the flask. So PCl5 decomposes according to the reaction. So the first thing I want to do if I'm given equilibrium amounts is to create an ice table and to put all my equilibrium reaction in my ice table. And then I go into putting information. It says right here the initial amount, and I want it in concentration, so I'm going to take moles divided by liters, which is pretty easy. It's the same value. And then I'm also going to put PCl5 in there. So PCl5, these two amounts are given initially. Obviously, I do not have Cl2, so I'm going to put 0 for the initial amount. I know at equilibrium I'm going to have all amounts present. So that means I'm going to be making a certain amount of the Cl2. And it tells us how much is going to be made at equilibrium. So that's why I know this is the amount, and thus this is the amount that changes as well. Which means I can work backwards to say this is the amount that forms because it's a 1-to-1 ratio. And then this is the amount is going to react. So I'm going to minus this amount, and again, 1-to-1 ratio. All the ratios fit the stoichiometric ratio that I see here. At equilibrium, I just subtract, add, and then add, or however much I make that is stated I would have at equilibrium. And then, so these are all the amounts. I take my expression and make my expression, which is products over reactants. I get the equilibrium amounts, which is these two products, multiply them, and divide it by the reactants. And this is my KC for this problem. Now I'd like you to work through FRQ 3 and 4. In FRQ 3, you won't be given an ice table on a typical problem. You'll need to create your own ice table. So highly recommend if you're given amounts at equilibrium, you want to make sure you ice it out. This is a KP problem. I can tell because I see atmosphere, and thus KP is played out in this problem rather than KC. This problem, go ahead and again set up an ice table and get yourself going with the ice table. Okay. Where the first 3 units were all conceptual based learning, we're getting into equilibrium, and from here on out we're going to do a lot of problem based learning. So we're solving problems like these, and icing it will definitely help you get in the habit of it and make sure you organize your data as you ice your reaction. And hints like equilibrium is enough for me to know to set an ice table. In FRQ number 6, once again, ice it as needed. And then go ahead and when you get to this last part, just understand and compare these two equations and go, oh, it looks like it's either double or halved or flipped. And then go ahead and manipulate the K constant so that you can, or the K constant of the original equation, so that you can find the K constant of this equation. And when we say manipulate, we're talking about manipulations include if you flip an equation, you take the reciprocal of the K constant. If you double the equation, you're going to be squaring the K constant. If you half the equation, you're going to be square rooting the K constant. If you're adding equations, you're going to be multiplying the K constants. Now we reach solubility product, and this is an equilibrium, so that's why you see K. And SP stands for solubility product. Ionic compounds are soluble in water. We know that. The degree of solubility for ionic compounds vary from one compound to another. So a chemical equilibrium can be represented to show the amount dissolved of the salt at equilibrium. Solubility rules are good for solutions of a certain concentration, usually anything greater than 0.1. But anything less than 0.1, we're looking at systems of equilibrium that are that require calculation. Okay. So here's a solubility table. If you look at the x and y axis, as you always should, this is the solubility of a salt in 100 grams of water, and this is temperature. So different salts, like sodium chloride, is going to be more or less soluble as temperature rises if to make what is called a saturated solution. So all along this graph is the saturation level of sodium chloride as you increase in temperature. So this tells you how many grams of, about 35 grams of sodium chloride would be needed to dissolve in 100 grams of water in order to reach equilibrium, which is the saturation point. Above that amount, if you add more than 35 at a certain temperature, you're really dealing with a supersaturated solution. Below that amount is going to be an unsaturated solution. So once again, all along potassium nitrate's curve right here is the saturation point, the amount of the salt that you would add in 100 grams to make a saturated solution at those temperatures. Below is unsaturated, above is supersaturated. And I'll do one more again just to make sure you understand it. Here you have calcium chloride. This is all the saturation point, the amount of solute that you, or the amount of salt, calcium chloride you would need to add in 100 grams of water to at certain temperatures to reach a saturation point. Above it is supersaturation. Below that curve, or less, adding less of the calcium chloride is going to be an unsaturated solution. So the point of saturation is where you hit your equilibrium. You reach equilibrium. Now, how we represent an equation, an equilibrium equation, is we take the salt, the solid salt, and we show the dissociated ions, the cation and the anion that gets dissociated off of that salt. Assuming this is all in water, but water isn't in this reaction because it's a pure liquid. And you'll know that it won't impact the equilibrium system. But we do know how much water we're adding in certain cases of the solubility. So you're adding a specific amount in order to measure how much of that salt would be dissolved to make a saturated solution. Once again, the case B is the solid salt and the dissociated ions that make that salt. What we're going to do is model what a case B or a saturated solution would look like for silver chloride as well as silver sulfate. A reminder that solids do not affect equilibrium, so you'll see some solid in here, but you won't see it affecting the equilibrium state that's in the solution. Okay, if you were to, of course, add a solid to stress the system out. So let's go ahead and I'm going to start off by lining up my solutions. And there's water in here, but I'm really going to just represent the salt, the solid salt, and the ions that make up that salt. So this is what a saturated solution would look like. You'll have a little bit of salt, a little bit of the salt, and some of the and some dissociated ions. Likewise, here you have on the right side for B, you have silver sulfate, and you have 2 silver ions for every 1 sulfate ion. Now, both of these salts are quite insoluble salts. These are insoluble salts. And because they're insoluble, there's a degree to which they are going to dissolve. Insoluble doesn't mean that they do not dissolve at all. It's just a degree to which they will be soluble versus insoluble. There's a very small degree of solubility, and so that so they have there's an equilibrium system with those insoluble salts. For equilibrium to establish, there must be some ions from the dissociated salt, and there must be some salt in the solution. So be aware that there's some solid salt and the dissociated ions that make up the salt. So let's get into the expression. The expression for solubility of any slightly soluble ionic compound in a saturated solution, once again, it's usually an insoluble or slightly soluble salt, represented as a ratio of products over reactants raised to their stoichiometric coefficient. But really, there's no products. It's only reactants. So the products, there's only products, no reactants. And there's no reactants because you're dealing with a solid salt. And so that's why we only include the 2 ions, the cation and the anion, in the K-SV expression, raised to their stoichiometric coefficient. So it's the same ratio. The only thing is you won't see any reactant because the reactant is a solid. If you have a small KSV value, it means the salt is less soluble for that similar ionic compound. We're really comparing when they have the same number of ions, dissociated ions. If you have a large KSV value, it means it's more soluble. That salt is more soluble for a similar ionic compound with the same number of ions. Let's take a look at the table on the right. So here's a bunch of ionic compounds that are insoluble or slightly soluble salts, and they have a KSV value associated with each of them. Usually, since K is temperature dependent, once again, notice how they set the temperature to be 298 Kelvin, which, by the way, is interpreted in degrees Celsius as 25 degrees Celsius, room temperature. All right. So the first question is, which salt, silver chloride or silver sulfate, is more soluble in water? Explain. And recall that we're talking about the same number of dissociated ions, and these do not offer the same number of dissociated ions. One has 2 dissociated ions, the other one has 3 dissociated ions. So we can't compare directly from the KSB values unless we actually go into the molar solubility calculation for both ionic salts. In other words, we set up an ice table and we do a molar solubility calculation to see who is more soluble. And so that will be later on when we start doing calculations. B, which silver chloride or silver iodide is more soluble in water? Explain. And if you look at their values, silver chloride is 1.8 times 10 to the negative 10th. Silver iodide is 8.5 times 10 to the negative 17. It looks like silver chloride is more soluble because silver chloride's Kb is a higher value, which means there's more dissociated ions. That completely makes sense, hopefully, because it is about the dissociated ions. A higher Kb value means this salt is more, silver chloride is more soluble than silver iodide. Degree of ionization and the units for that. There's two vocabulary words that you really have to understand when you get into this category Kb. It's molar solubility and solubility. They mean pretty much the same thing, only you're dealing with moles here versus grams, okay? So molar solubility is the grams of the solute, which is the ionic salt, dissolved in 1 liter of a saturated solution, and the units for that is in molarity. Solubility is grams of solute dissolved in 1 liter of a saturated solution, and so the units is grams per liter. So be aware that they're really the same thing. One is converting moles to grams, or the other one grams to moles. So you can easily maneuver between the two degree of ionization units, which is molar solubility and solubility. Okay, so we're going to calculate the solubility and the molar solubility. Recall that solubility is really the grams per liter of the salt that would make that saturated solution of that salt. And then molar solubility is moles per liter, which is molarity in the end, so capital M also. So we're just calculating how much of the salt, the AgCl, and in another instance, the silver sulfate will dissolve to make a saturated solution. Okay? So, and we're going to use the equilibrium constant because the equilibrium constant is, in fact, what this occurs at the saturation point. So it's the ratio of the products, which are the two ions, over the reactants, which is a solid, and the concentration of the products at equilibrium. So that's why we're using the K constant. So we set up an ice table. We have our two ions that make up our salt. And then we start off saying, hey, you know what? This solid is a solid, so I'm not really going to be caring about how much I have initially. I want to know how much is going to dissolve, so I'm going to have a change. But I won't have the equilibrium amount of silver chloride is insignificant because it's a solid. Now, however much I lose or dissolve of the silver chloride is how much I'm going to make of these two ions, dissociated ions. And so 0 is how much we start off between the two, and x will be how much we have at equilibrium. So once we have the equilibrium amount, we can plug the silver ions, which is x, and the chloride ions, which is x, and multiply them together. And so you set them equal to the Kb constant, which you should find on the chart that started off this section right here on Kb. So there's a chart in the previous pages on page 16 that gives you the Kb for silver chloride. And then solve for x. Once you have x, you really have to know what x represents. X is really the molar solubility. How much of this salt, how many moles of this salt will dissolve to make a 1 liter saturated solution? And so that's exactly what the amount is. X is here. And then I can convert my x, which is molar solubility, into solubility by converting moles to grams of silver chloride, and that will give me my grams per liter. Notice I have my moles per liter and my grams per liter. This is called my molar solubility. And this grams per liter is called my solubility. Look at the graph at the beginning of this when we started talking about solubility product equilibrium. You'll notice that the solubility is grams per liter unit-wise. Okay? And so we do the same thing. I would pause and try to work through by yourself silver sulfate, but I do have my work here already, but pause and work through it yourself. Okay, Now that you've unpaused, you'll notice that silver is twice. So the change is going to be 2 times. And so when you do go ahead and find the equilibrium amounts, you also know that when you write the expression, you'll have to square the concentration of silver. So that's why I always do write the expression. And I'd like you to make a habit of writing always the expression so that you know what is relevant in your KSB reaction as well as expression. So again, I looked up my KSB value of silver sulfate using the chart on page 16, and then I notice my concentration of silver is 2x. I raise it to the square it because that's what it says right here. I have to take the silver and square concentration and square it. This is the silver concentration. I square it times a bisulfate, which is x, and then of course reevaluating this, simplifying this, you get 4x cubed. And so you have to solve for your x. Once you get your x, you will have what is called molarity, molar solubility, which then can be converted to grams per liter. And that's what you're seeing here. Go ahead and now work through the rest of these problems. I do expect you to write the expression as a very good hint. Always write the expression out for any equilibrium reaction if needed. And then secondly, ice it if you're seeing concentrations being required to be found. So if you're trying to solve for concentrations or even grams of a certain amount, you actually should be setting up an ice table. So go ahead and set up an ice table for these two. Squeeze in there, please. Write your reaction very carefully. It's always the salt and in equilibrium with the dissolved ions that make up the salt, which is silver and bromine, or bromide ion here, barium 2+ ion, and iodate ions as well. Be careful with the 2 here, dissociated. Make sure you account for the coefficients, okay? Go ahead and do these 2 problems. Okay, let's go ahead and go over example number 9. In example number 9, you see that 3.0 times 10 to the negative 5th grams of lead 2 arsenate will dissolve in water to make a 1 liter saturated solution. So once again, saturation is my cue for understanding that I'm looking at equilibrium. So the word saturation means I'm at equilibrium. And here's my salt solution. This is my ionic salt, my insoluble ionic salt. It's not very soluble, or slightly soluble ionic salt, if you want to call it that as well. So it gave you, in this problem, you're given how many grams it would take of the salt to dissolve to make a saturated solution. So in essence, you have what is called the solubility, the grams per 1 liter. Grams per 1 liter dissolved to make your saturated salt. And I'm going to call that my solubility. Now, KSB is all in concentrations of molarity, so it's nice to take my solubility and convert it to molarity, and that's what I'm doing here. I'm taking my solubility and converting it from grams to moles per liter. And essentially what you normally would expect to be X in the chart, this is your molar solubility. Now I decided to still set up a ice table so you can see how this all logically works out. So in your ice table, as usual, you set up your salt and the ions that make up your salt in equilibrium, and then you realize that you do have your molar solubility already. It's 3.3 times 10 to the negative 8th. There must be an error somewhere here. It must be, my error is to say that this is 10 to the negative 8th and 8th here. Okay, so from there, you realize that it's 3 times the molar solubility to figure out how many the ions of lead 2+ at equilibrium, and it's also 2 times the arsenates or the molar solubility for the arsenate's concentration. So these are all the concentrations once you multiply these out, okay? And it's also reiterated right here. And to find KSB is just to write the expression as always so that you remember what you're cubing or squaring here. And so you plug in your concentration at equilibrium and you cube the lead concentration, and then you plug in the arsenate's concentration at equilibrium and you square that. And that will give you your KSB in the end. Now we get into something called the common ion effect, and exactly as that suggests, the word common ion and the effect of the common ion. And this really goes back to Le Chatelier's principle, so let's go ahead and see it conceptually right now. Upon adding a salt, what you do is upon adding a common ion, what it does to the salt's solubility is it decreases the solubility of that salt in the saturated solution. And so let's see how that plays out in Le Chatelier's principle. So here's my KSB reaction. Here's my KSB expression. If I add a common ion like a cation, so I add a salt that has that cation into a solution that is saturated of this salt, what it does is it pushes the equilibrium going the reverse direction, which means that decreases the amount of the salt that will dissolve. And so pushing that way will decrease the amount of salt that will dissolve. It will lessen it. And we're actually going to calculate that to see how much the molar solubility decreases as a result of adding a cation or an anion that is shared in this equilibrium reaction. So because we're not necessarily at equilibrium, we're reintroducing this idea of Q. So you have something called QSP, where you're comparing your Q to your KSB and seeing where you're at in the reaction. Oftentimes when you add or Q helps us to understand where we're at in the equilibrium. If Q is less than KSB, the ratio of the initial concentrations of products to reactants is too small, and that means I need to pump up the products so that I can try to get for Q to equal KSB. So the forward reaction is going to be favored, to be shifted, and that will then lead to the formation of my salt. In other words, what I have is a solution that's unsaturated. No precipitate is going to be seen during that time. When Q is greater than KSB, equal to KSB, you're at equilibrium. So you're at a saturated solution, and concentrations of initial concentrations are at equilibrium. And so you'll see some salt, some precipitate, and a lot of dissolved ions as well, or some of the dissolved ions at equilibrium. Here you have a situation where Q is greater than KSB, which means there's a lot of dissolved ions, and those dissolved ions means you have a large K or Q value. So the reaction is going to find a way to reverse because there's so many dissolved ions. You're going to form some salt, and that formation of the salt is what makes the solution a supersaturated solution, and it's going to form. You're going to see a lot of precipitate coming out of solution during that time. So these are three different scenarios describing the level of saturation for your solution and whether precipitate will come out of that solution. Let's go ahead and venture into some calculations with a common ion as well as understanding why. So there's the conceptual part of this, okay? So here I have silver chloride. I like to use silver chloride. It's a simple insoluble ionic salt, and it forms silver ion and chloride ions. Now what happens initially by adding sodium chloride, which is a common ion, the common ion that's coming off of sodium chloride is in fact the chloride ion here. And upon adding that chloride ion, what you're going to do is you're going to cause your chloride ions initial amounts to be 0.1 because that's how much you have initially. And of course there's no silver ions because there's no not yet, any silver ions, and you're trying to figure out how much will dissolve as a result of this common ion being added. Notice at equilibrium you're adding the common amount, the common ion's amount to the chloride amount that you have at equilibrium, and also silver ions. You set up your KSB expression, and then you'll notice that you'll get into your multiplying the two equilibrium concentrations of silver and chloride. Now, here's where you start to make an assumption. You're going to make an assumption that X, right here, is smaller than this value that's being added to the X. So it's going to be much, much smaller. In other words, the solubility is going to be because this is an insoluble ionic salt, the solubility is going to be small already, but it's going to be even smaller. And so because of that, you can then do your math with ease. What I mean by that is now instead of 0.10 plus x, now it's just 0.10. So you can just plug that 0.10 in, still multiply it times the silver's concentration at equilibrium, which is x, and then that makes an easier mathematical problem to solve for x. Once you solve for x, I see that x ends up being a pretty small number. So your assumption earlier that this number is much, much smaller than 0.1 is true. Look how small this number is. You calculate and determine what is called the grams per liter, which is the solubility. So you're really trying to calculate the solubility. And then you multiply it times the volume, which is 1 liter. I forgot that step. So multiply by 1 liter, and that will give you grams in the end. So that's where you get your gram unit in the end. Now, notice the solubility here for silver chloride, when you add a common ion called sodium chloride here, 0.1 molar of it, you are going to see the solubility go down. And how I know that is I had calculated this silver chloride without any common ion earlier, and we knew from earlier that the silver chloride solubility is 1.9 times 10 to the negative third. But as a result of adding sodium chloride to the silver chloride, notice how this value decreased. From here to this value, there's a significant decrease. And that decrease is called the common ion effect. And that's because adding chloride is going to lessen the amount of silver chloride that will dissolve because you have already some chloride in solution. So that is going to shift the equilibrium to the left in the reverse direction, favoring the reactants, which is the salt. And that will mean that there would be resulting in more salt production rather than dissolving of the salt. It's resulting in more solid silver chloride production rather than the dissolving of salt. So less of the salt will dissolve. Okay? Let's go to example number 11. In example number 11, if you read it carefully, you're always reading your problems carefully. Take a pause if you need to. You are looking at silver chloride and how that silver chloride, whether that silver chloride will precipitate out or not when you add silver nitrate to sodium chloride. In other words, you're doing the precipitation lab from last year where you're mixing two solutions and you're actually quantifying whether that solution will yield a precipitate or not, which means I'm going to have to calculate Q, and I'm going to have to calculate my Q and compare it to my KSB. A precipitate will only occur if Q is greater than KSB. No precipitate will form if Q is less. You're at equilibrium, so there is some precipitation, so you're at a saturated solution when that is the case. So let's look to see what to do in a problem like this, where again, you're looking at adding two different solutions and you're seeing if a precipitate will come out of that solution, and you're quantifying that instead of qualitatively looking to see if a precipitate occurs. So the first thing you want to do is, because you're adding a certain volume of one solution to a certain volume of another solution, what you are doing is diluting all the concentrations of all the ions that make up that solution. What ions are we concerned with? We're concerned with the ions that make up the salt, the insoluble salt. So I'm going to dilute the ion's concentration. And to dilute is to use M1 V1 equals M2 V2. I'm going to write that on the side. And we're interested in knowing what the M2 is. So to rearrange this equation, you're going to take M1 times V1 over V2. Now notice how this is a ratio. You're just really ratioing the old volume to the new volume. The old volume to the new volume, and you're multiplying it times the initial concentration. And that's precisely what I've done. Here's my initial concentration of the silver ion. And then here's this is my old volume, and then this is the total is my new volume, which is 60. So then my new volume is 60 milliliters. Old volume, new volume. So you're ratioing that and to get the newly diluted solution. Now you're going to do the same thing for the chloride ion. So here's the concentration of chloride ion. You're going to ratio the chloride ion's initial volume, which is 40, divided by the total volume, which is 60. So this is your V2 is your 60 milliliters. And there you go. There gives you your new concentration of chloride ion. Now multiply, write the expression out as you normally would, but now call it Q because you don't know if you're at equilibrium. So multiply these two out. The concentrations of the silver ion and the chloride ion. Again, you don't know if it's at equilibrium. You get the value of Q. So you compare your Q to your KSV value right here. And upon comparing those two values, you see that Q is going to be a larger value. So Q is bigger than KSV. So there's a higher Q. A higher Q means that the reaction is in fact going to precipitate out. So you're going to see a huge amount of ions because Q is the ions that make up the salt. So there's enough ions for you to be able to precipitate out the salt. Okay, so there will be a precipitate. And here is a model to show for the precipitate. You're going to see a good amount of solid coming out of the solution as a result of enough ions present to do so. So now you have to figure out what the concentration is of the silver ion in the solution at equilibrium. And so your initial amounts will be your Q amounts, which are these concentrations. And you start off with the Q amounts. Now, the lesser amount is going to be the one that's kind of limiting this reaction, even though it's not quite a limiting reactant situation because you're going to have all species. It's an equilibrium reaction. But you know that all the amount of the minimum amount, which is this amount right here, silver, is what you're going to have. And so you're really going to find out how much chloride ion is resulting from that reaction at equilibrium. So once you find out how much chloride ion, you can plug it into what is occurring at equilibrium, which is your KSV constant, and then you can figure out your KSV. Now, I know it says 0 right here, but it's going to be near 0. That's why you really want to know how much of the other anion is present so that you can figure out how much silver ions is currently present, though it's near 0. Okay? I know it's counterintuitive to say, hey, it looks like it's 0, but it actually is close to 0. So we're really trying to find the silver ion concentration at equilibrium. Thus, we use the KSV. Work through these two problems right here, FRQ 11 and FRQ 12. FRQ 13, it looks like it's a mathematical KSV problem. With your insoluble salt right here, and the solubility of that salt is given to you in grams per liter at 25 degrees Celsius. So go ahead and ice this problem. For sure you want to ice it so you can see what's happening in this problem. Let's go on to example number 12. In example number 12, you're given the KSV for both lead 2 chloride and lead 2 iodide. And you're looking at you're finding the molar solubility for A and B, which is simple. You set up your ice table. You don't know how much is going to dissolve your salt to make your saturated solution, so you call it X. And of course, you're going to make a certain, however much dissolves is how much of the dissociated ions, depending on their stoichiometric coefficient. And there you've got your equilibrium concentrations. You can set up your equilibrium expression as well as the constant, and then go ahead and solve for X, which is how much of the salt that will dissolve. So lead to chloride that dissolves. I really want to always emphasize the definition of what molar solubility is, how much of the salt, the solid salt, that will dissolve. Once again, we want to always learn and make sure we understand how to draw. So again, you're going to have some lead to chloride solid, very little of it, as well as some lead 2 plus ions and 2 chloride ions for every 1 lead 2 plus. And you're making a saturated solution. Likewise here, same thing. You're seeing your solid lead 2 iodide. You've got lead 2 plus ions that are dissolved, as well as iodide ions that you see in here. Example 12, part C. Go ahead and read the question out loud to yourself to make sure you understand. So what you're doing is you're taking a solution of lead 2 nitrate and you're slowly adding it to a 1 liter solution containing 0.15 moles of chloride and 0.010 moles of iodide in constant volume. So I have a flask here. I try to visualize what's going on as a way to help me to see what I'm doing. So once again, this 1 liter flask. This is a 1 liter flask. And in this 1 liter flask, I already have 0.15 moles of chloride ions. And I also have 0.010 moles of iodide. I need to figure out how much lead to nitrate that I would add to see who would precipitate first, basically. And the precipitate we're looking at is lead to chloride, so lead with chloride, and lead to iodide. So essentially, I am going to discount the nitrate ion because it's a spectator ion. And I'm really looking at lead 2 plus coming into this solution, Pb2 plus here. And I'm figuring out between the two anions who will precipitate first. And so I'm going to go to the equilibrium constant to see who will reach, who would need less lead before it hits equilibrium, which, by the way, past that point would be when the precipitate occurs. So that's when QSP is greater than KSP. So I'm going to see which one will give us a lower lead concentration. That lower lead concentration will, I know, be reached first by that substance, and thus a precipitate will come out of the solution first before the other anion. Okay, so I'm going to calculate, and that means ice table. So I'm going to set up an ice table for both lead to chloride and lead to iodide. And I'm going to set up as normal, and my initial amounts would be however much molarity of chloride and iodide I have already in my solution initially. And then I'm going to see what happens to the solubility, molar solubility of both, and ultimately solving for X, which is the lead 2 plus concentration at equilibrium. So once I do that, I notice my 2x here, coefficients, always taking a look at my coefficients, 2x here, and I add up my initial and my change, I get my equilibrium concentrations. I start off with my expression. As always, I never skip that step because I want to make sure that I don't forget to square what I need to square, don't forget to cube what I need to cube if there's a cubing involved. And then I plug everything in, including my KSP values given to me. And then I get my concentrations at equilibrium, and I raise my anions concentration to the second power. Now this raising of to the second power leads to a pretty complicated trinomial problem, which quadratic formula I could go to, but I'm going to use what is called the assumption method. I'm going to assume x is quite small compared to 0.5 that you're added to here. You can also call it 2x if you want. And so that zeroes, if x is small, that zeroes out this x and giving us only 0.15 to square. And then you solve for x. Solving for x is my lead concentration, which is what I want to figure out and compare. And I'm going to do the same thing with lead to iodide. Once again, I'm going to use my assumption method, and then I will then solve for my lead to concentration. Now, don't forget to validate your assumption, and I've done that because I really want to make sure you are validating it. And so I take my concentration, my x value, and see how it compares to my 0.15, divide it, times it by 100, and I see that it fits the 5% rule, less than 5% rule. So it's perfect. I've assumed it was a valid assumption. And the same thing here goes, I assume small, x is small, and then I validate and I see that, yes, I am within the 5% range, less than 5% range, that is. Notice between the two leads that I see here, which one produces less lead is going to be the one that will reach equilibrium first, and not only reach equilibrium first, that substance will also precipitate first as well. So the lower amount is looking like this one. This is less lead 2 plus right here. With that means that lead to iodide would precipitate first if it produces less, it needs less lead 2 plus ions. And so that's my explanation right here. Of course, I didn't put my data in, and I should put my data in. I did it down here where I talked about my evidence, which is since lead to iodide needs a lower amount of this value compared to this value, lead to iodide will precipitate first. So I really do want to put my two evidence right here in my explanation as I explain. So class, I have given you all the different ways to calculate, all the different ways you'll be asked to calculate concentrations at equilibrium or KSP at equilibrium, or determining what will precipitate first. So you're essentially given an example of every single possible way, and now it's your turn to just really work through these FRQs, make sure you understand what you're looking at, model if you need to model, because modeling obviously does help us to understand what is going on and how to logically calculate what you need to calculate. So go ahead and work through the rest of the FRQs in this section. Here you have a KSP problem, and I have a 4-star to this, which means it is this is the most difficult of the problems that you'll have to come across. But we did talk about how to determine what salt precipitates first and how to calculate it. So please make sure you go through example number 12, which we talked about in order to calculate this part right here. The scenario is very similar to example number 12. FRQ number 16, make sure you work through this as well. Once again, it's more calculations. Don't forget to either model when you need to model. Make sure you write the expression out so you know that you're going to square the F minus concentration at equilibrium. And then just plug into ice tables where you need to plug into ice tables. So set up your ice tables as a way to help you to do any equilibrium problem. Finish up FRQ number 17, and you are to complete all the AP questions and set problems.